Hello, it's Mr. Zafiro back here again as we're trying to do the best we can under the circumstances. I'm going to ask you because I don't think everyone's following along with this, so please text, call, email, Snapchat, Tic-Tac-Toe, whatever apps you kids are using. Get in touch with some of your classmates. Tell them I'm active on the website. Some of you have been working away at it, and I really appreciate it. Some of you have even been asking me questions. I appreciate that. Remember, this is sort of the clearinghouse for questions right here. We click on it, and this is what we call a discussion thread. So we click on physics questions, and look, Ryan posted something kind of cool. So did Brandon. And I replied. Jackson posted a question. Then I answered it right here. Okay, and if you want to key in on it as well, look, you can reply to my solution. Waleed asked the question here. Can you take up question 11 and 12, 11 and 13? So here they are. I've answered question 13. It's a video. I've answered question 11. It's a video. Section 4.5, practice question 11. Section 4.5, practice question 3. So I have been following along with what you've been posting in the questions. Just like when we were in class and you would come in the morning, sir, and you give us a little bit of a heads up on the homework we did yesterday. Yeah, of course, let's take it up. It's the same thing, only at a distance. So please get involved in that. Please, 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 please. All right, so today's lesson is about simple harmonic motion. So there's going to be some motion involved. Harmonic means that it's moving back and forth with some repeated regularity, with a known frequency, period, things like that. And the frequency, the period of the motion, how it's moving back and forth is rather simple because this is our, only your second physics course. So here's some examples of simple harmonic motion, and I've posted this link in today's announcement. So here's an animation of some type of film or layer, a surface, and it's moving up and down, up and down. So it's moving up and down, and it's actually undergoing a restoring force to pull it back down. Here is some type of pendulum. The restoring force that pulls it back down is gravity. Here is a speaker operating. It's moving up and down, simple harmonic motion. It would be the magnetic field pulling the surface of the speaker back downward and pushing it forward. That's how speakers work. Here is the classic one right here, a mass on a spring. There you have it, moving up and down with some period, some frequency which are known and are constant. It's simple harmonic motion. It's a spring. Therefore, there's a restoring force. We just went through a lesson on this. And the restoring force on the spring will follow Hooke's law, meaning that the restoring force is linear. That's why it's called simple harmonic motion, because linear is a pretty simple function. Simple harmonic motion. Let's take a look at this with greater detail. So we still have our friend the spring. This graph right here is going to show us what is the x position of the mass at the end of the spring as it undergoes simple harmonic motion due to a linear restoring force. Simple because it's linear. Here is a graph that's showing us the y component of the velocity. There's no x component, but nevertheless it's y as it's moving up and down. So there's a graph of that. And here's a graph of the acceleration as it's moving through this simple harmonic motion. So we're going to play it through, and as you see here, it's quite sinusoidal. All right. Now what I'm going to do is I'm going to go through step by step. So there, see, I'm pushing one step, next step. Okay. So when the object when the object is at the top of its y motion, as high as it can possibly get, so the mass is going up, 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 and then it stops, and then it's going to start coming back down. So when it's at its maximum displacement from the rest position, its velocity is 0 and the acceleration is at a maximum. So let's keep on stepping through here. Notice how the y position, the y velocity, and the y acceleration are changing. Now, when the object is back to 0, okay, when the object is back to 0, that means the object is at the rest position. That means the spring has no compression and the spring has no stretch, no expansion. Y position 0, rest position. At this point right here, look, the velocity has reached a maximum and the acceleration is 0. And that makes sense that the acceleration is 0 there, because you remember acceleration is dependent upon force. The acceleration is dependent upon force, meaning if the acceleration is 0 here, the net force is 0 here. All right, let's keep going. As it goes through, goes through, goes through, goes through. And now it's as far down as it's ever going to get. So it's falling down and it's going to stop and then bounce back up. So this is at the moment it stops its downward motion. All right. And at that point there, it's as far down as it's going to get. Its y velocity is 0. Y velocity is 0. And the acceleration is at a maximum. Its acceleration is at a maximum there. So it's going to fall down, stop, stop, and then spring back upward again. And there you have it. And we can play through there showing this. This is a graphical look at simple harmonic motion, the position, the velocity, and the acceleration. Very helpful to keep these ideas in mind as we move forward with this. We're now going to move to a note on this. All right, our note on simple harmonic motion. There is a version of this note available that I've put on today's announcement. So you don't have to worry about scribbling this down quickly. So simple harmonic motion. An example of that would be the simple pendulum. Why is it called simple harmonic motion? Because it involves a linear restoring force. It follows Hooke's law. If it was not a linear restoring force, and there are certain situations like that, it would not be simple harmonic motion. It would be some other type of harmonic motion. And they do exist, but they're not part of this course at the high school level. So what have I drawn here? Well, welcome to my world here. And I have a wall, a floor, and I have a mass attached to a spring, and that spring is attached to a wall. And I'm going to pull this mass over, and I'm going to let it go. And I'm going to assume there's no friction here. So what's going to happen is this mass is going to move back and forth and back and forth and back and forth. It's going to undergo simple harmonic motion. Now, let's talk about the displacement. Right here is what we call the rest position. X equals 0. At this spot right here, the spring is neither compressed nor stretched or expanded. Nothing. Rest position. Over here is what we call the positive X max position. This is as far as it's going to get over. Positive X max. So it starts here, swings through the 0 position, and then it gets to this spot right there. And that spot there, that's as far as it gets over in the negative x direction. So we call this the maximum displacement in the negative x, or negative x max. Now, this is very similar to something we learned in grade 11 when we were talking about vibration. This positive x max, this negative x max, in grade 11, you would have known it as an amplitude. So the object goes over one amplitude, the object goes back two amplitudes, the object goes over to here, three amplitudes, and the object comes back four amplitudes. And we learned that four amplitudes equals one cycle. One cycle, going all the way back to stuff we learned in grade 11. What else do we know? Well, if you think about this, the object moves from the rest position over to x max, and then it stops for an instant, and then it starts to go back the other way. So the velocity here is zero, zero velocity right there. Now, this is very similar to when you throw an object up in the air. It moves up in the air, then it stops, and then it starts to fall back down. Very similar idea. The restoring force there, if you want to think about it, would be gravity. The restoring force here is the spring. So it stops for an instant, flies back through here, right here, as it's being pulled by the spring back. But now it reaches no compression, no stretch. As soon as it starts to go past the zero spot, it's going to start to compress the spring and therefore start to slow down. So when it gets to x equals 0, this is when the object is moving at the maximum. On this side here, it's being pulled back by the spring, pulled back by the spring, faster and faster and faster and faster. Gets to here, now it starts to compress the spring and starts to slow it down. That means right in the middle here is where we have maximum velocity. So the object continues, it's slowing, 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 slowing because it's compressing a spring, it's compressing a spring. Finally, it slows down so much, it reaches its maximum displacement on the negative side. It doesn't have enough velocity, if you will, to compress the spring any further, and it stops. Velocity is equal to 0. All right, well, let's continue here. We know that the mass at the end of the spring is experiencing a restoring force. We know that from the work done by Hooke, and the restoring force is linear and it acts on the object. There's no friction, so what we can say is that the restoring force is equal to the net force. There's no other force acting on it. And of course, we know that F net equals ma. Well, the restoring force from the equation we learned the other day is negative kx is equal to ma. So if I rearrange this equation, I get acceleration is equal to negative kx over m. Well, when would the acceleration be the largest possible? The mass of the object is not going to change. The spring constant is not going to change, but the position changes. So you get maximum acceleration when x is at a maximum. That's what I wrote down here. Acceleration is at a maximum when you're at the the positive x max position and the negative x max position. That's where you get the biggest acceleration. When would acceleration be 0? Well, when x is 0. When you put a 0 in here, the acceleration is 0. So this is kind of new for us kids because most times you've dealt with accelerations that have been constant. That is not the case here. And the reason the acceleration is not constant is the restoring force is not constant. The restoring force depends on the position. That's what makes this a little bit more complex. Let's take a look now at this from energy considerations. And we would have that the total energy of the moving mass at the end of the spring is equal to the kinetic energy it has at any particular part of the motion, because we see that the object moves back and forth and back and forth. That's motion. It's going to have kinetic energy. And it is connected to a spring. As that spring gets stretched and compressed and stretched and compressed, it will have varying amounts of elastic potential energy. And this total energy is conserved. Why am I saying that it's conserved right now? Well, we are ignoring friction at this point. We said that the coefficient of friction on the surface was 0, and that's a good place to start. We can add friction later because we like complex things, okay? And we'll get to it, but not now. Let's just deal with no friction. All right. Okay. Let's keep on thinking about energy considerations here. At the end points, so at positive exposition max and negative exposition max. At those endpoints, we have established that the object is not moving because it's going to stop at the endpoint and start moving in the other direction shortly. So it has no kinetic energy. All the energy is elastic potential, which would be a half K. And in this case, instead of putting X max, I'm going to put in A for amplitude, because another way of talking about maximum displacement is amplitude. There you have it. Going back to a grade 11 concept. So that means at the endpoints, the total energy is equal to a half K, the spring constant, times the amplitude squared. What about at the rest point when x equals 0? No compression in the spring, no stretch, no expansion in the spring, right smack dab in the middle. X position is 0. Well, if x position is 0, no expansion, no compression, no stretch in the spring, the elastic potential energy would be 0. But it is moving at that point, at the rest position. So it has a kinetic energy, and it would be a half the mass of the block times v squared. And I'm going to give this special velocity, since it occurs at the 0 position, I'm going to call it v naught. We don't call it v0, we call it v naught. All right, so this is the speed of the object when it's at x equals 0. So that means that the total energy of the object undergoing simple harmonic motion, that object at the end of the spring that we're talking about here in our little thought experiment, would be half the mass of the object undergoing simple harmonic motion times the speed that it has at the rest position squared. So what can we do now? Well, look, here's an expression for total energy. Here's an expression for total energy. Total energy is conserved. They have to be equal to each other. So let's equate them. Half k amplitude squared is equal to half m, the speed of the object at the rest position squared. The halves cancel out, and I'm left with ka squared and mv naught squared. Now I can divide each side by m, and now I have an expression for the speed of the object squared in terms of the spring constant, the mass of the object, and the amplitude. I can also, if I want, I can rewrite this like this. The speed of the object at the rest position is equal to root k over m. And if I root an a squared, it's just going to give me a. There you have it. All right, so we just finished a discussion about the total energy of this object undergoing simple harmonic motion at the endpoints and at the rest position. Well, that's cool. There's nothing wrong with that. But what about at any point in the motion as it's going back and forth between positive x max and negative x max? So let's say that at any point the object will have a certain amount of total energy, which will equal its kinetic energy at that point and its elastic potential energy at that point. And let's put in the expressions for those. Put in the expression for kinetic energy and put in the expression for elastic potential energy. And we know that has to equal the total energy. Now, let's take advantage of the fact that the total energy we know will equal half kx squared, because it's the total energy it has when it's at maximum displacement or at its amplitude. we can now take a look at this expression and cancel out all the halves. That cancels out, cancels, cancels. And we're left with ka squared is equal to mv squared plus kx squared. What I'm now going to do is bring the kx squared over here because I know I can factor out a k. And I have k factored out. So I have k times bracket a squared minus x squared and bracket is equal to mv squared. What I now can do is divide both sides by m. And I have k over m. And then in the bracket, a squared minus x squared is equal to v squared. And now what I'm going to do, and this is going to sound a little bit strange, but I'm going to factor out an a squared. So I factor out an a squared out of here, and I'm going to factor out an a squared over there. Wait a second, there's no a squared in there. Well, there's a way around that. If you factor out an a squared and it's not in there, you have to replace it in the denominator then. Don't believe me that these two are equivalent? Multiply the a squared back in. Look, if I multiply the a squared back in, I get a squared. If I multiply the a squared into here, there's an a squared in the numerator and the denominator now. They'll cancel out, and I'm left with x squared. So this is a little mathematical sleight of hand, a little mathematical trick. Why did I do that? I did that because I wanted to create the expression ka squared over m. Why did I want to do that? Well, let me show you. Ka squared over m is equal to, oh, v naught squared. Isn't that convenient? And there we have it. I've now replaced ka squared over m with v naught squared. What have I created? Well, we have created, I should say, an expression for the velocity of the object undergoing simple harmonic motion at any point. I can now tell you what the speed of the object is at any point by knowing what its speed is at the rest position, knowing at what point it's at, and knowing what its maximum displacement or amplitude was. That is a very powerful and convenient equation.